Assalamualaikum and a very good morning. My name is Muhammad Mirza bin Musa. My matric number is EA180544. Okay, so today I will present to you about additional theory for the lab report, which is losses in pipes for fitting. Okay, the resistance to flow in a pipe network cause loss in the pressure head along the flow. The type of head loss across a pipe network consists of first major losses, which we can call it H major, or the second one is minor losses, which we also can call it H minor. Okay, for the major losses, it is referred to the losses in pressure head of the flow due to friction effect. Major losses can be calculated by using the Darcy-Weisbach equation. Okay, as we can see on the report, H major can be calculated by using the formula F times with L to the power LV to the power of 2 over 2GD. We also can find the HL or the HF by using lambda times LV squared over D squared D times 2G. From the equation, we can know that the F and the lambda is the friction factor, and the L is the length of the pipe segment, V is for the velocity of flow in the pipe, D is the diameter of the pipe segment, and G is gravitational acceleration, which is 9.81. The friction factor which is the F, can be calculated by using many types of formula, such as Blasius formula, Colebrook, White equation, or Swami-Jain equation. For this type of pipe, the formula that we use is Blasius formula, which is F equal to 0.316 times Reynolds number to the power of negative 0.25. Okay, the Reynolds number can be obtained by using this equation, which is Re equal to rho Vd over mu. Okay. The mu is the dynamic viscosity that can be assumed as 1.005 times 10 to the power of negative 3 kilo meter second. Okay, for the minor losses, okay, that's all from major losses. Now we continue to the minor losses. Okay, for the minor losses, the presence of pipe fittings such as bends, elbow valves, sudden expansion or contraction causes localized loss in pressure head. This is this is also can be termed as minor losses. Okay, the observed head loss is due to the loss in the object itself plus pipe friction. Okay, the HL for the minor losses can be found by using this equation, which is HL equal to K times V squared over 2G plus lambda times LV squared over D 2 times V. Okay, where K is the loss coefficient of the pipe fittings under consideration. To determine the suitable value for the lambda, we can refer the calculation from the major losses part, which is from the top one, this one, because this is the same as the major losses. So, or we can use the Moody equation. The equation, we doesn't conclude it in our report, so we just use by the calculation from the major losses. Okay, minor losses also have been expressed in terms of the equivalent length of the straight pipe, which is L equation that would cause the same head loss as the fitting under consideration. H minor can be found by using this equation, which is K times V squared over 2G, or F times L equation times V squared over 2 times G times D. Or we can find the LE equation by using K times D over F. Okay, the head measured can be calculated by convert the pressure difference using the following equation. HL is equal to P1 minus P2 over Pg. Okay, P1 and P2 are respectively the upstream and downstream pressure in Pascal. Okay, next we move on to the objective. The objective of the experiment is to determine the losses across the fitting in a pipe network. To study the loss coefficient, which is the key for a range pipe of fittings, including several bands, contraction and enlargement, and a grade valve. The last one is to observe the difference between major losses and minor losses in pipes.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Saiful Farabi bin Ahmad Zakwan. Now I'm going to talk about the procedure of this experiment. For the first experiment, we need to measure the head losses across all the fittings. So, step 1, we need to connect the inlet to the bench supply and the outlet to the volumetric tank. Connect it by using hoses. Step 2, we need to open the bench valves, the gate valve, and the flow rate control valve, and make sure that all these valves are fully open. Step 3, connect the another hose to the air connector. Step 4, start the pump. Step 5, close and open the gate valve and do it for several times. This step can make the removal air bubbles process to be easier. Step 6, when the system is truly free of all air bubbles, reduce the flow rate by closing the flow rate control valve slowly until it be open in about 25%. Step 7, check the readings on the manometer height. Step 8, close the ball valve. Step 9, by using a stopwatch, measure the time needed to the water fill 5 liters in the tank. Start the stopwatch when the water level reaches 0 and stop the stopwatch when the water level reaches 5. And then record the time taken. Step 10, open the ball valve to drain the water in the tank. And last, step 11, repeat the step above, starts from step 6, but increase the flow rate by opening the flow rate control valve to 50% open and then 75% open and then 100% open. And we are done for the first experiment. So the second experiment, we just need to measure the head loss through only the gate valve. So here this experiment. For the second experiment, we don't need to repeat the removal air bubbles process because the air bubbles already gone. So step 1, we need to start the pump, and step 2, open the bench valve and flow rate control valve and make sure they are fully open. Step 3, we need to open the gate valve to 0.3 bar. Step 4, close the ball valve. Step 5, measure the time needed for the water to be filled 5 liters in the tank. Like the first experiment, start to counting the time when the water level reaches 0 and stop count Stop to counting the time when the water level reaches 5, and then record the time taken. Step 6, remove the ball valves to drain the water. And step 7, repeat the step above. Start from step 3, but increase the pressure on the gate valve to 0.6 bar and 0.9 bar. So the whole experiment is done.
Assalamualaikum warahmatullahi wabarakatuh. My name is Manul Hakim. Our group have to do an experiment about losses in pipes that is lost across pipe fittings. I would like to talk about the result and the graph that we have achieved. So first thing first, the result. We decided to divide it into two parts. That is raw data tables, and the second one is result table. Um, So in the raw data tables, we have part A. This is part A and part B. Part A is head loss across pipe fittings. Okay, let's start with part A first. Uh, in the video, there are four tests that have been done in this experiment, and the volume collected also is the same um for the whole experiment, that is 5 liter. But the time taken to collect 5 liter is vary from test 1 until test 2 is vary. And then we have a type of fitting, that is enlargement, contraction, short bend, 90-degree elbow, 45-degree elbow. And then let's move to part B, head loss across gate valve. So we have 3 head loss across gate valve, that is 0.3 bar, 0.6 bar, 0.9 bar. The volumes also is the same with part A, like part A, that is 5 liter. Uh, but the time is vary. The more greater pressure on the head loss, uh, the smaller the time taken in second. And then we go to the result table. Uh, Same as the raw table, have part A and part B. But the difference for the result table is we have calculated the flow rate, that is Q, velocity, for Q over pi d, velocity head equal to V squared over 2G, and then delta H, which is H1 minus H2, H1 minus by H2. And then this calculation um, will be reviewed by our friend Muhammad Shami in uh, in the second of this video. And then the part B also is the same. We have head loss the 0.3, 0.6, and 0.9. Also have the calculated flow rate Q and velocity V equal to 4Q over pi d. Also, and have the velocity head, but we have added up this um, head loss coefficient, that is K, equal to delta H over divided by V square over 2G. This means delta H divided by this, and we get the answer. Okay, let's move to the graph. There's a graph part A and part B. Part A is this table graph, which is we do the velocity head versus delta H. So this is the graph. As we can see, the blue is the 90-degree elbow enlargement is orange contraction is the gray one, and then so on. So as we can see, the pattern of the graph is directly proportional. This means that velocity h is directly proportional to the delta h. And then we move to the graph on part B, that is flow rate Q versus head loss coefficient K. That is one reading only. That is this one flow rate Q 2.48. This one, this third, versus by K. So we have this type of graph. So I will continue on the conclusion at the final of this video.
So now I'm going to discuss the observation that we got while watching the experiment videos. So the first thing that we realized when we were watching the videos is the system contains an air in it, and the air should be removed from the system to get the accurate measurements. So the second thing that we can observe from the videos is the closing and opening the gate valve step in procedure. So this step is to make the removal air bubbles process to be easier. So this is kind of tips to remove the air bubbles. So the third thing is the readings on the manometer. The manometer would show the same reading for all the fittings when there is no flow rate. And the fourth thing is in this experiment, five types of fittings have been used, which is enlargement, contraction, short bend, 90 degrees elbow, and 40 degrees elbow. So when the flow rate started to apply, the manometers would show the different measurements for every single fittings. So that's all the observation that we got from this experiment. So thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shamil Kushairi bin Sari. Today I am going to explain you about the calculation for energy losses for fittings. And for the test one, we will find the energy losses in sudden enlargement. First, we need to find the flow rate. To find the flow rate, the formula for flow rate is Q equal to volume per time. So we have find it earlier. So in this formula, we find the viscosity. For the viscosity formula, V equal to 4 Q per pi d. So we input the value V equal to 4 times flow rate. This is flow rate, which is 5 liter per 21.765 second times 1000 divided by pi diameter. The diameter for the fittings is 0.299, and the viscosity we will get is 3.073 exponent negative 3 meter per second. And to find the head loss, we the formula to find head loss for sudden enlargement is V1 minus V2 squared 2D. So we put the value for every and we will get the head loss equal to 3.0073 exponent negative 3 meter per second squared and divided by 2 times gravity 9.81. So the head loss that we get for sudden enlargement for test 1 is 4.813 exponent negative meter. So next, we will find energy losses in sudden contraction. So we must find the flow rate, and the flow rate for this test is same. Then we put the flow rate inside the formula for viscosity, and V equal to 4Q D, and we put the value 4 times flow rate per pi diameter. The diameter for fittings in contraction is 0.251 for test 1, and we get the value for viscosity equal to 1.165 exponent negative 3. So to find the head loss, the formula is head loss equal to Vc minus V2 and squared per 2g, 2 times gravity. So the Vc is not given, which is 0, minus the viscosity from here, and squared the viscosity, then divide by 2 times 9.81 is gravity, and the head loss we will get is 6.918 exponent negative 8 meter. So next, for energy losses in short band, just the same as before. We find the viscosity, and then we put the value for V equal to 4 times flow rate 5 liter divided by 21.765 times 1000 per pi diameter. The diameter for short band fittings is 0.219. So the viscosity that we get is 1.336 exponent negative 3 meter per second. So the head loss formula for band is K V squared over 2G. So we put the value inside unknown, and for the K for short band we put 0.3, and V squared, the viscosity that we get here, put 1.336 exponent negative 3 times power of 2 divided by 2 times 9.8. So the head loss that we get from for short band is 2.729 exponent negative 8 meter. So G losses in 45-degree elbow for the test 1, same, we find the viscosity. Then after we got the viscosity, we put the value in head loss formula, K times V squared per 2G. So the K is the coefficient loss coefficient. So loss coefficient for 45-degree elbow is 0.2. So we put in 0.2 in for K, and times the viscosity per 2 times gravity, which is 9.81, and for the head loss we will get 2.117 exponent negative 8 meter. Next, for the formula for all fittings is same, but the changes is in time. So for flow rate we must recalculate and replace value for time to find the new flow rate. So for the new flow rate, 5 liter divided by 23.89 second times 1000. So for the viscosity, V equal to 4Q per D. So for the we put the value, and then we get 9.189 exponent negative 4 meter per second. For the head loss, the formula is still the same from the earlier test. which is V1 minus V2 squared per 2G. So same. Then the answer, the answer that we get the head loss for sudden enlargement in test 2 is 4.304 exponent negative 8. And energy loss in sudden contraction V equal to 4Q equal per pi d. It is the same but with different times taken. So we just replace the time for flow rate and then recalculate everything. For viscosity, we will get 1.070 exponent negative 3. And for the head loss, we got 5.835 exponent negative 8 meter. Same as for energy losses in short band by using 23.89 second for the time to find the flow rate. And next for test 3, which is we use the time taken uh, used in energy losses in sudden enlargement in is 29.49 seconds. So the formula is same to calculate head loss. The test 4 we 39.92 seconds as for the time taken. Then we calculate it all. So I am going to explain you about the discussion for our experiment. From the result of the experiment, we found that the lower the head loss, the higher the velocity of the fluid. The higher the velocity of the fluid, the higher the flow rate of the fluid across pipeline. From the graph A, we can see that the higher the velocity head, the higher the head loss in the pipeline. The slope of the graph for graph A shows that it is slowly going up. For graph B, we can see that the higher the head loss coefficient, the higher the flow rate of the fluid. Also, the slope of the graph for graph A is slowly increasing. So for the accuracy percentage of our data, we get 60%. This is because of some error happen when we do the experiment, and one of the error that we did during the experiment is that we misread the reading of the flow rate meter on the machine. This is because the flow rate meter reading is placed at the lower part of the machine, so it make us to very hard for us to read the, not very hard, but we have to actually what, parallel our eyes with the reading. So it is hard if the reading is at the lower part of the machine, so it is very hard to actually see the reading. And the other error is that the ball valve cannot hold the water inside the drain to collect the water efficiently. We can say that the ball valve is actually more smaller than the hole for the drain, so the water can collect pretty much. So reading our reading that our data from the experiment is slightly different from the calculated one, which this is this may affect the result for the manometer reading across the pipeline.
The conclusion for this experiment is that Measuring head loss to different type of pipe span could help us to estimate energy coefficient for each transition. By recording the time taken, volume of water collected, and height of manometer reading, we could calculate the value of flow rate Q, velocity head, and head loss coefficient K. We can conclude that this experiment is minor losses in pipes because it have the sudden expansion and contraction. So the loss coefficient K must be determined through each situation. So all we have to say is lesson from this experiment um, have been learned, and that is all from us. Thank you.